Right, so the mission statement for the longest time is to build the world's most performant quantum computers to solve the world's most challenging and impactful problems. But I extend this now to all these technologies, right? Ultimately, there are grander ideas of how we can marry different various quantum technologies to do and explore areas that have just been unexplored, right? Quantum computers will look at intractable and theoretically intractable problems for classical compute, but we can also think about how we start to network these things with quantum sensors and use quantum information from quantum sensors to do some kind of computing on that. And these are unexplored spaces. It's a very exciting time to be in this space. So you can go to the next slide. On the quantum computing front, we've been building devices since around 2015. 2019, we put the Harmony system on the cloud. So we were one of the first quantum computing companies to put a quantum computer on and make it accessible on the cloud through an AWS bracket. Since then, that Harmony was like a test bed system. It's been decommissioned. It was like 11 qubits. We were still able to do some interesting things, but if you do quantum computing, you're probably well aware that you can simulate 11 qubits on your laptop pretty easily. But it's still interesting for us to develop a technology and try to learn about how it functions, the errors, how to characterize the machines. And so we got a lot out of that system, and people were able to access it pretty early on. Since then, we've been developing additional machines. We have the Aria, is the 25 qubit system. Forte is 36, and Forte Enterprise is also 36. Those are all available now via the major hyperscalers, so you can access on AWS Bracket, Microsoft Azure Quantum, or Google Cloud's platform. So you can run on these machines now, or you can access directly through us on our APIs, and you can test these systems now. And the scope of this is we've been building these systems with the intent of being able to deploy them in data centers. This is something that's somewhat unique to IonQ as a company versus some other quantum companies, is we've always had this vision that we would build distributed quantum computers, and then we'd be able to put them into data centers with a data center form factor, so you could just put your quantum computer right next to your high performance supercomputers that you have sitting there in your data center, and it just fits all together. So that's what Forte Enterprise really is. It's just like Forte, but it was built with a data center form factor, and we've deployed it. So we have one sitting at a place called Quantum Basel in Basel, Switzerland, in one of their data centers now. And we are deploying another one in Tennessee. That's really exciting, and I'll show you a little bit about some of the things that we're doing in Tennessee that we're really excited about. Beyond that, we are going to make accessible the next generation system Tempo. It'll be about 100 qubits. It'll have some added features and characteristics, nice things that you can test and play around with. And then beyond Tempo, we'll start to move away from what we've been doing, which are these long chain linear arrays of trapped ions, to an architecture that we've adopted from a company that we acquired out of the UK called Oxford Ionics, that has this what's called a quantum charge coupled device, the QCCD architecture that allows them to transport ions around in individual potential wells and isolate the computations that you do with them that way via these microwave electronic controlled gates. So that's the 256 system, and beyond that we'll scale very rapidly to, I would say, relatively large numbers of qubits. If you pay attention to this space, that's a very aggressive roadmap compared to what everyone else thinks that they can do by 2030. So hopefully one of the things that you'll get out of this is, my hope is that you're convinced that this is actually viable. We're not just making it up, that we really think that we can get to this point. Okay. So you're probably familiar with the different modalities for quantum computers. There's trapped ions, superconducting, neutral atoms, photonics. There's vacancy centers. There's all kinds of different ways. If something shows some kind of quantum properties, you can make a quantum computer out of it in theory. There are people that are doing this with whole molecules, trying to make a molecule into a qubit. We choose trapped ions for a number of reasons that I'll go into. Let's just go ahead and go into that. Yeah. So this list on the side here are some of the primary reasons why we chose trapped ions. One of the things that's not mentioned here is that trapped ions have been tested for doing computation for maybe the longest stretch of time compared to some of the other modalities. Chris Monroe, the founder, did some of the earliest entanglement gates between qubits back in like 1995. So that's 30 years. It's pretty well understood how to use trapped ions for qubits. Why do we like them? Because we don't have to manufacture them. So we don't have to deal with manufacturing tolerances and all these things that could potentially go wrong when you try to build chips to make systems. Nature just makes them perfectly for us. They have long coherence times, high fidelities. We can construct a universal gate set. I won't belabor this too much, but this here is why we picked trapped ions. Now there you see in that sort of animation is the approach that we've taken to date, which is to trap and hold a long chain of ions. I would say, arguably, IonQ is the best at controlling and computing on long arrays of trapped ions. And we've been able to really extend those chains to like a theoretical maximum. There's only so many of these ions you can put into a chain and get the most out of them. So this is what we've been doing, and the way that we do computational gates is we would operate on them with these what's called Raman lasers to individually address each of the ions within that chain. And we have a universal gate set, so we can do everything that you would do with, potentially like universal quantum computer. Okay, but we're transitioning now. Why are we transitioning? Well, we could still do some of the long chain operations, and maybe in the future there's some reason to still hold ions in long chains to do some of these operations. But for scaling, there are a lot of engineering considerations and operational considerations for while you are holding long chains versus operating on short chains. One of the really nice benefits of the Oxford Ionics architecture is the way that they do computational gates is no longer via lasers. So it's really great because lasers are cumbersome and are really hard to work with. And so what we'll do then, and what they've demonstrated, is that they can do all the computational gates via these oscillating magnetic fields, right? So they'll have a stacked chip, and within that chip, in the sort of underlying layer, they'll have what is like an AC current line with an antenna. Let me see. This right here. So on the surface layer, you have ions that are held in their traps, suspended over the surface of this track, right? And here on the sides, this is intended to depict like DC electrodes. So in the QCCD architecture, the way that it works is you can use RF rails to create quadrupole fields that trap your ions. You make like potential wells for each of these ions for your qubits. And then the DC electrodes, you will vary the voltages of those. Since this is ionized, varying the voltages of these external electrodes will allow you to transport these ions along this track. And there's another nice feature where they use shim electrodes to transport the other direction. I'll get to that in a moment. And beneath that, there'll still be some laser operations, but it's only for like state preparation and measurement. And that's something where there's much looser tolerances on actually like using lasers that you could put on picks in a layer of the chip and then have it deliver a beam directly to an ion in that zone to prepare and measure those ions for computations. You can go to the next one. All right, so this is from the paper that they released, and this is really exciting to me for a number of reasons. Now, what I mentioned before is you have those DC electrodes, and in this depiction that shows that you're able to move them up and down in this X direction, right, along this track. But they also have the shim electrode that gives them the ability to move and translate the ions in this Y direction. Now, the scheme that they did for this paper is really interesting, where they say, in the center of this track, I'm going to effectively create a null space for that field. So if my ion is sitting in the center of this track, it's not feeling anything from the magnetic field. So whatever I'm doing with that AC current line, creating that field, the ion's not feeling it. Great, you need that to just keep it still and stable, right? Now, with the shim electrodes, it allows them to translate into this Y direction, and this is actually the way that they do the computational gates. So that oscillating magnetic field has a sharp gradient, and when they translate the ion into that magnetic field, the amount of the computational rotation for that gate is directly dependent on the magnitude of that magnetic field that the ion feels. Does everyone kind of follow how that works? Okay, so that's really interesting. So they could do that. You could imagine a scenario then, and they demonstrate this, that you could take multiple ions sitting somewhere on this track. You can separate them by some maybe considerable enough distance, say some microns apart to where there's negligible crosstalk. And you can translate them into that magnetic field. You could do it all together, and then have that AC current line create that magnetic field and do a global gate on all of them at the same time. That's really great, that's exciting. There are other modalities that can kind of do this, like neutral atoms. You can kind of fan out the laser and do something like a global gate. But what's a big differentiator here is you don't have to translate the ion to the same amount of the magnetic field, right? I can translate an ion a little bit and then another one a little bit further, and they'll feel a different amount of rotation. So that really adds to the parallelization that you're able to do in running computational gates on ions with this specific architecture. There's no other architecture quite like this. So I hope that stimulates your minds a little bit for the types that want to program quantum computers, start thinking about algorithms and things that would benefit from this kind of nature. Yeah, so we can go on. So this is the idea of how we'll scale them. And hopefully it comes across as pretty straightforward. So what they demonstrated is they can do this with, I think they did up to 8 qubits on a track in that paper. But if they take what they call just like a unit cell, which is just 2 qubits, and then they just kind of modularize that, right? So they can kind of just repeat those unit cells. All along this meandering line is the AC current line. So you could just place those unit cells all along that, and then you could just replicate that around on this 2D array. So you can effectively take the technology you have, and you've proven out that with this technology, they demonstrated the highest 2 qubit gate fidelities of anyone in the world. It's at 4 nines, 99.99% 2 qubit gate fidelities. It's the world record. They demonstrated on that, and then all we do then is we just scale them monolithically on one chip. And the plan is to scale them up to 10,000 qubits on one chip. Okay? So what happens after that? This is our technology roadmap that we just released. So what you see here is around this area, 64 to 100, that's like the tempo system. Around here, this 256 system will be the first demonstration proving out that like a larger version of the QCCD architecture that I showed you a moment ago, right? And then we'll scale up to the 10,000 qubit chip. After that, you'll notice that this number then doubles and then goes up by a factor of 10 and so on. And so what's happening here is this is the point that we'll actually start to photonically interconnect our quantum processing units. That's the scheme to scale this. We could probably go higher on these just singular chips, but if you're familiar with quantum computation, there's a lot of trade-offs in that space of whether or not you want to do it all on one chip or move to distributed quantum. In theory, I think every modality has to ultimately move to distributed processing units. Okay, so that's how we'll move. Here's our error rates. We can go into that in a moment, but let's get moving along. The other enabling technology that we have that will allow us to do this connection for this distributed quantum computing is another company that we acquired. As previously, some folks had AWS. They did a lot of work with like Michiel Lukin at Harvard, if you're familiar with him. He was one of the founders of QEra. They constructed what is like a photonic memory module. So it's a silicon vacancy center where they're able to asynchronously take in photons, store them as memory, and that allows us to then, via some switch, connect multiple processing units together to do distributed computation. Does that make sense? All right, we can move on. So this is the idea that we're starting to put together, right? Ultimately, the big utility in being able to network these things is to do this distributed quantum computing. But there's a lot of other things that are really interesting in networking as well. The things that you're probably more familiar with are like secure communications. You know, quantum can help. It can really hurt cryptography. You know, it can also help to support and make cryptography and encryption more robust. So we're exploring that. And trying to show with our other kind of secondary technologies how we can create this larger picture to start to build what will effectively be like a quantum-enabled internet. Okay, so we built that. We've been demonstrating a lot of things on the ground, and you can see in this depiction we're starting to think about how we move into space.
And so that's where Capella Space comes in with our bespoke low Earth orbit constellation. And so we design, launch, operate, and commission our satellites all in-house in about 18 to 24 months. We operate in both mid-inclination and sun-synchronous orbits that'll cover both your polar regions as well as your populated regions of the globe, which gives us a high revisit rate coupled with the fact that synthetic aperture radar is agnostic to day-night cycles as well as auto cover. So it allows us to be able to do 24/7, 365 coverage. We've also designed our tasking interface with the customer in mind, being able to have you as the user directly task our constellation and download the data from it in as little as about 3 to 6 hours. Not only are we a trusted mission partner for industry, government, as well as civil applications, and we offer trusted end-to-end expertise and world-class talent on all of our product lines. We also offer an analytics partnership program where we're able to bring in AI and machine learning companies to build products around our imagery. So we're able to offer things like vessel and vehicle classification, as well as ground cover characterization. So you as the analyst are able to more rapidly distinguish between a carrier or a destroyer or gravel versus sand. So Capella plus IonQ, what Capella enables is that ground to space and space to space quantum communications and networking segment, because we're able to fly optical communication terminals as well as space qualified clocks on our bespoke platform towards things like position navigation and timing in GPS denied environments. We're able to resolve defense-grade provenance, protecting customers' data and their most critical information from devastating cyber attacks, as well as working towards a scalable quantum architecture for really all users and enabling intelligence in any environment.
All right, perfect. So we're starting to put some of these pieces together, right? So we've been talking about the computing, talked a little bit about secure communications, and I'll elaborate some more on what that means for us, what we're actually developing at IonQ. And now we're starting to think about how do we integrate with satellites, so how do we start to build, you know, on land, how do we think about doing things in the sea, in the air, and ultimately in space. For quantum internet, you need to be able to touch all the major arenas, right? Satellites being, you know, a key critical component to being able to do that. So we start to integrate now with Capella. We're moving into this quantum repeater technology. That's the memory modules that I told you about. One really nice feature about those is they help to act as memory modules to connect quantum computers to do distributed quantum computing, but they also act as repeaters that allow us to extend network lines. So you may be aware that trying to send photons over fiber optic lines, there's a lot of loss. And you would potentially lose all the gains that you would try to get trying to connect over these long lines. This quantum repeater technology will allow us to extend on land, like via fiber optics, to many, many more kilometers. And then there's this later dream that comes along with something called blind quantum computing, which is very interesting. Raise your hand if you've heard of blind quantum computing, you're familiar with this topic. Yeah, I didn't think so. It's newer to me too. I think it's really interesting. interesting. So it's this idea that you take advantage of the encryption that you're doing via these like QKD methods or something like that. But what you'll do is, if I'm a user and I want to send my circuits to a quantum computer, say it's sitting somewhere in a data center, I don't have access to it, but I don't want whoever sits there and holds that quantum computer to know what I'm trying to do. This is something pretty unique to quantum computers in the way that we can encrypt the data as the user, send it as a job to the quantum processing unit, and whoever is sitting there hosting that unit has no way to find out what it is that you're actually computing. Okay? So that's one application area, and then there are others that come in this form as we try to think about networking these systems. And so now I want to go into a bit of where we're at in trying to connect quantum computing devices, right? So we're actually doing the demonstrations of these things now. We have multiple systems, and now we're trying to actually show how we can use this ion-photon entanglement to connect one quantum processing unit to another via, you use some transducer. This is like a quantum frequency converter that allows you to go from the bandwidth of light that you're working with for, like, say, trapped ions to go to telecom wavelengths. You use a ring resonator to help to extend the line and the memory. You use a Bell state analyzer to differentiate between the Bell states, right? And then you can show that you have this level of entanglement between your two distributed units. Okay, so this is one scheme. This is an early scheme that we're using to just demonstrate we can do this connection and build this distributed quantum network. Okay, so this is sort of how it works. There's this idea that, and this is really how we do readouts for trapped ions, right? The ions, when they're excited and they de-excite, they'll emit photons, right? When they de-excite to certain states, that you can dictate that de-excitation will dictate what type of photon, like how it's polarized. And so you can horizontally and vertically polarize your photons, and you get this entanglement between the photon and the ion that you can then send over a fiber optic line, have it share with another compute node. So this is something that we've demonstrated. We've shown that we can do ion-photon entanglement, and recently we showed that we can do this down conversion to the frequency of light for the telecom wavelength. So if you go to the next slide, this kind of shows you what that looks like. So 493 nanometers is roughly what we're working with for the wavelength of light for like a barium ion that we use for computation. And we need to get that to 1351 so we can send that over a fiber optic line. So this is what we very recently just demonstrated we can do. So we can do this conversion. Theoretically, then we can send our photons as far as we need to, because these fiber optic lines are as long as you make them, as long as you have something like a repeater here. So moving past Bell state analyzers to something like the memory module that I showed you before allows us to extend those lines. And so finally, you can take this as like a rough sketch of what this might look like if I had two quantum processing units. I have my quantum frequency converters, and I try to filter for my polarized light. I have some non-polarized beam splitter, and then I have these detectors for my polarized light. And this is the thing that we're demonstrating now. We need to demonstrate that we can do the entanglement with the ion and the photon, send the photon over to the next QPU, do the entanglement over there, and then start to share those. Okay, so if you go to the next slide, I'll talk you through a little bit of how this works in theory and what we're trying to demonstrate. So say here I have theoretically these two QPUs, right? The blue dots represent computational qubits. Those are ions sitting waiting to do some form of computation. And I want to connect them together, so I do this ion-photon entanglement with those light, like cyan kind of dots there. And what I'll do is then I'll like synchronously connect those two together, and then I'll try to entangle them with what are like memory qubits, those red dots there on each of the QPUs, right? So I'll do an entanglement with the memory qubits, and then what I need to do is I need to do a swap with those, what we call like interconnect qubits, memory qubits, or just really interconnects. I'll do a swap with those. If you go to the next slide, once I do that swap, I can then take those, transport them, and connect them and entangle them with the remaining ions in each of those processing units. Once I do that, I have two fully entangled operational quantum processors. Make sense? Is anyone excited? You guys don't seem excited yet. I'm very excited about this. It's a big deal. So, I mean, you can imagine then this idea of scaling quantum computers, just working with a handful, but you start to connect these things and you can achieve that full entanglement, then you're really just limited by other like engineering concerns like latency loss, things like that, but these are things we're mitigating with the technologies that we're developing. Okay, so there's the mitigation. So the Bell State Analyzer has to take in these things synchronously. And so this was a major bottleneck for trying to connect multiple quantum processing units because you have to have the same time consumption of these photons coming in to the analyzer. And what we're showing, there's the obvious issues with doing that. If you lose a photon, your connection fails, you have to start all over. But if you can do this asynchronously and store them, like I was saying, via the silicon vacancy centers, then you don't have that problem, right? You can kind of just store them in memory and use them as you need to, right? Part of the issue when you're trying to do this is you're sending single photons of light. If you're familiar with photons, they're bosons. They don't like to interact with things. They just lose, they get lost all over the place. They're really hard to control. So you need to create like a lot of redundancy with that. You need to entangle several and try to store them so you can use them when you need to make sure you get the entanglement that you need. Does that make sense? Right? Okay. So that's what we're showing that we can do. And now we're starting to show that we are really putting together all the necessary components and capabilities to construct everything we need for a secure quantum internet, right? So we have photon sources, we show we can do down conversion, we have detectors, we show we have these memory modules to make quantum repeaters, we have switches, we can do time synchronization in a number of different ways, and I can talk about that maybe after this if you want to. We're looking at doing distributed quantum computing, and we look pretty heavily at also doing like QKD or some kind of form of like secure quantum communications in a couple of different ways. So one way that we do this is through entangled photon sources. So that's where we have a photon source that entangles the qubits and it sends as photons, it sends them out to the sender and the receiver. So they each get one, right? And then you have your classical channel that allows them to communicate with each other, to tell each other, well, if I measure in this random basis, you measure in this random basis, what did we actually measure in the agreement? Then that's what they use for their key. The prepare and measure is...
May I ask a question just there?
Oh, sure.
The translation between the qubits and the bits in that measurement stage, is that worked out already?
The translation between
the ions on going from qubits to bits.
Oh, sure, yeah. So, I mean, anytime that you do a measure on these things, it effectively works like a bit, right? The moment that you try to measure your qubit, it's in like a bit-like state. It's either 0 or 1. So you're just using binary. It's the same for all the computation that we do. At the end of the day, what you get is a bit string.
Right, and that's all clear.
Yeah, so I'm about to show you in a moment, but this technology exists. This is demonstrated, we're using them, these systems are deployed, people are doing QKD in real networks.
Because the whole system you're showing is entirely quantum. I mean, it's still at the qubit stage.
So it's not entirely quantum, there are classical channels here too.
Okay.
And in this case, you're doing this like sort of like entangled photon source, so it's kind of a different flavor of doing QKD because you do have that like entangled quantum channel versus this prepare and measure where it's really just kind of comparing the basis states. But ultimately, yeah, it's going to be translated to classical bits, and that communicates like how you actually make the keys. Right, okay. So there's trade-offs, there's pros and cons to each of these, right? The nice things with the entangled photon sources, theoretically, that seems to be like the most secure form of doing this, right? You have this entangled system. If an eavesdropper tries to come in and steal any information, it's going to become very apparent immediately. It'll collapse the state. and then Alice and Bob, or the sender and receiver, will know what happened. The issues with that is it's lower yield. You're not going to be able to do as many of these, create as many keys as quickly. So the nice thing in the prepare and measure situation is you can create a lot more keys, you can generate more, you have a higher yield. And so you can start to imagine maybe there's scenarios where I would have some preference to use this versus this, and then we need to figure out where those would be. So you can go to the next slide. So we have built these systems, they are deployed, we have existing quantum networks all over the world. There's networks that use these Clavix XGs in Korea. We have the entanglement version of this with this Bohr 4 quantum network here in the state of Tennessee. So that's actually how IonQ got started and embedded in the state of Tennessee, is working with UTC and EPB, is a utility company in Chattanooga. We deployed a Qubitech company we acquired, deployed this quantum network. And when the quantum network, there's a number of different components that you could put in that. This BrinkQNet is just one box. It's an example to do this quantum entangled key distribution. Okay, so we can go to the next slide. And this is what I hope everyone is the most excited about, because this is right in your backyard. So if you guys wanted to get to a point where you want to test on real quantum networks, so be connected to a quantum computer and really get your feet wet on this, this network exists. So there's a network, the Bohr 4 network, that's sitting out in Chattanooga, where there's talk of trying to connect it. So this is a metropolitan network. So this is the thing that you start with, right? It's like a small local area network, you can think of it. And so you'll start to want to think about like how we can extend this to other cities in the state of Tennessee, like Knoxville or Nashville. Okay, anyways, so this is deployed, and we can certainly talk about how you guys can get access to this and start working with it. Yeah?
So what are the costs of operating large amounts of data of your quantum computer at its current state versus a traditional computer?
The costs in what sense, like?
If I'm processing, I have a lot of, let's say I have a lot of like genomic data, for example, that
Right.
I have to go and process. What are like the cost comparisons in operating on one of your systems versus other competitors that are non-quantum based?
Sure. So it's not a totally fair comparison right now because of the numbers of qubits that we're operating with on quantum processors, right? In the most naive case, you would do like almost a direct comparison with like your qubit acts as like almost like a transistor, just like bits, and then you would encode your information that way and like do like a basis encoding, and that's terrible because then you have effectively 100 transistors or something like that to work with, whereas in other classical processing units you have billions. So. But there are all these different encoding techniques that one can use to try to get classical information into the quantum computer, and then you get to work in this exponentially large Hilbert or vector space to do all your computation in. So that's a really important question, and it is a bottleneck for a lot of the devices that we work with in what we call the noisy intermediate scale quantum computer era that we're in right now, small quantum computers that are still kind of noisy. And for certain applications, we won't be doing really, really meaningful things until we can get to much larger scales, depending on the type of data. One example I'll give later is we can ingest like images. So we can ingest different types of data, whether or not you're going to ingest some massive corpus of data. I mean, probably not. You could do it iteratively, and then you have to ask yourself, am I actually saving money or time, or but it's a really good question. Yeah.
Let's say we want quantum node here in National.
Yes.
What are some challenges of doing this, connecting it to networking, checking, apart from just digging a lot of ground and putting cables?
So the networks that they developed are capable of working with dark fibers. It's not ideal. Ideally, we would lay our own fibers, and there's an added cost that comes with that. But they can work with existing very dark fibers. So if you already have optical fibers that connect to something, and there's a way to connect somehow via some like utility provider maybe that you have, you could do that connection, and it just will be less performant. but it's a good way to get started.
So it's where you're visible.
It's
It's where you're visible to connect that node to.
Yeah, I mean, it's not a major impediment. I think the fact that that network exists expedites the process vastly for, anyone in this area wanting to build a metropolitan network and connect out and start to do real meaningful experimentation with these networks. Do you have a question?
Yeah. I know you mentioned like 2 slides ago that QKD isn't compatible with quantum repeater technology. Does that mean that
The prepare and measure QKD.
Yeah, prepare and measure.
The integral one is.
Yeah, so
Yeah.
like, do you think that there's any effective future for prepare and measure QKD in long distance quantum communication, or do you think the future is only QED?
I mean, I don't know. I don't know how that technology can grow to do that, to extend to longer lines. I think the application really matters too. Like, you're certainly not going to use it for distributed quantum computing, but for some other secure comms, I don't know actually what the extent, like the killing distance is for doing prepare and measure QKD. It's a good question. Yes.
I was just curious about the quantum memory they're using as like a repeater for fiber optic networks. What's the kind of like limitations of how far that can actually stretch your like quantum communication compared to doing stuff like QKD with satellites?
So, and typically you think about it like, I can theoretically go up to like 50 kilometers without it. Then I can double it with a repeater and go up to 100. And then I can just keep adding repeaters. So that's what makes it like, no longer at the same limiting factor, because you could just add in more repeaters and extend that line theoretically as much as you want. What the latency and like loss and all that, that's a different story, but you can do it. Yes?
So I understand why you use obviously QKD for communication and your internet between nodes, but why would you use it over classical communication encryption like AES 256 for just secure purposes? When that AES 256 is supposedly kind of quantum proof, or it could be if you just have increasing digits?
I don't know if I would say it's quantum proof. I think you could just increase the digits. I think the same method that works for AES 128 would just extend, just using graph research. You could still do it. So I don't know if I would say it's fully secure then, like it's actually quantum proof. I think that's still something, I don't know, maybe you know more about it than me, but I haven't seen anything that says this is definitively quantum proof. So I think it just depends on the applications. I don't think it's that you'll never use classical encryption for anything. There's some complementary nature to these things. And so it's very much like NIST has now these post-quantum cryptographic algorithms that are like being standardized, right? Or they have dictated that they should become the standard to protect against quantum attacks as these devices develop. And the thinking is that QKD will very much complement PQC at various layers, and it really depends on what you're trying to secure and why, and how truly secure you want that to be. QKD is secure because it's based on physics. Classical methods are secure because they're based on some mathematical formulation that maybe not now, but in the future could be reverse engineered. We've sure showed that there's a quantum way to break RSA. So I don't know how strong they'll be for the far future. But I wouldn't say it's just all classical encryption goes out the window. Maybe that's not what you were getting at. You just wanted examples.
Yeah, I was also just wondering, have commercial businesses or government organizations expressed interest in using QKD in like transatlantic communication or even like coast to coast?
I think there are
Like what use cases have expressed interest?
some of these things might not be in the public space as much. I'm gonna just leave it at that. So I think there are expressions of things that maybe just people aren't seeing in the public space, and you can imagine why. I'll leave it at that. Okay, so back to this grand story that I'm telling is we are showing that we can do these networks on the ground, right? Ultimately, we are building these quantum data centers, right, via these networks and quantum computers with distributed quantum computing. And what we could then theoretically do is, tie to some ground station, communicate with a satellite, and have a secure communication comm link between ground stations with satellites. And we can do that in a variety of ways. This prepare and measure QKD is one way. The entanglement distribution is another method. It's potentially, I think, oh, there it goes. Yeah, as a potentially more secure method, depends on what you're trying to do and what the issues could be with doing that entanglement in space. But there are options that we're going to start exploring and experimenting with. The nice thing about this is we get to experiment with it and see what works and what works well. Okay.
So that's where we've been talking about doing QKD and how are we, what are our plans for encryption of data, and that ties back to how is Capella protecting and encrypting customers' data today. And to be able to talk about that, what I first wanted to start with is examining how we currently do tasking on the Capella platform today. And of course, it starts with you, the user. So you're able to directly log into our system either via a console interface, or if you want a machine-to-machine connection for automated tasking, you can use a robust API architecture, and you can actually upload your tasking to our constellation. It'll be routed through the ground control segment. We partner with a number of ground control providers, including AWS, KSAT, and Atlas. And so from the time it takes for you to upload your tasking to get to the satellite is about a 15-minute cycle, which is how often our scheduler updates. The satellite will then collect over your area of interest and then downlink back through the ground station provider and deliver your data to you in about 3 to 6 hours, as I mentioned, on average. And so at each point, the uplink and the downlink, we encrypt our user data based on National Institutes of Standard Technology protocols. And so what this means for our platform is we are designing sovereign space systems specific to the customer in mind, doing things like concept of operations and operational playbooks, as well as using encryption protocols and key handling consistent with government standards, combining the automation and delivery with sovereign systems for our data as a service pipeline. And so we are really offering security you can trust in our cloud operations and uplink downlink cycles. What also differentiates Capella in terms of customer security is we're one of the few commercial satellite providers that has an active CMMC level 2 certification for handling confidential but controlled and classified information, and we are a trusted government partner with a facility clearance level. And so not only are we being very encryption and security minded, we're also pushing the boundaries of what you can do with synthetic aperture radar. And this is the part I like talking about because I just get to talk about imagery for 20 minutes. So we're doing a number of cool things with our satellites to be able to image faster and be able to collect more of an area with things like doing parallel strip map. So strip map is a very wide imagery product, between 10 to 100 kilometers in length and between 5 to 10 kilometers in width is our standard offering. But with parallel strip map, you can do multiple of those in tandem, either side by side or in length. So you're effectively capturing double the amount of imagery you would be able to do originally in a single pass. We can also do things like extending our squint angles. Squint refers to the ability of the satellite to look off broadside, because in SAR you're never looking directly at the ground, you're always kind of looking to the side, and that's an effect of how the radar works. But we're able to effectively look further off at an angle, and so that allows for greater control of where you want to image in a satellite pass and how far you want to image along that orbit. We can also do a number of interesting applications with our post-processing. So things like coherent change detection, colorized subaperture imagery, and interferometric synthetic aperture radar, which I'll talk more about in a couple slides. So as I mentioned, CSI, or colorized subaperture imagery, is where we can post-process an image and apply colors to man-made objects to bring them out of the black and white grayscale that you would usually see in SAR, And so what this does, it allows for greater distinction and for for better analysis of like some of those fine scale details, which I'll show. And so what analysts are able to do is they're more rapidly able to do like pattern of life analysis and decision making based on the imagery interpretation. Interferometric synthetic aperture radar, or INSAR, if you don't want quite as much of a mouthful, is where we can put our satellites in a super tightly controlled orbit. So effectively, you know where it's going to be at any single point in a pass. So the only thing that is really changing when you stack those images over time are going to be millimeter level surface ground deformations. So that's really helpful in applications for volcanic monitoring, if you're looking at volcanic activity. Similarly, if you want to do seismic deformation along earthquake faults. It's also really useful for surface moisture if you want to do like agriculture, especially in arid regions. Or even if you're interested in looking at ground deformation around city centers or large-scale buildings to make sure that there's structural integrity associated with those man-made structures. So as I mentioned, when we're doing INSAR, we really need to tightly control that orbit. So the plot to my left actually shows a 7-day orbit that we've done with one of our satellites in a demo. And so we're effectively keeping it in about a 250-meter tube. And you can see that that tube is highlighted in red. The actual green section is the real path of the satellite. And we can do, that's about down to 100, 150 meters. So we can actually keep our satellites more controlled than the tube we're putting them in. And so that just shows that we can accomplish INSAR with one satellite, and theoretically we could do it with the rest of our constellation if there was a demand for it. This is a example of CSI. So you can see at this naval base in Russia, the man-made structures have been colorized. There's no color scheme, it's just maximum contrast against the grayscale background that you would generally expect in SAR. But you can see in the pop-out to my upper left-hand corner, that ship, the way it's been colorized really helps to identify some small-scale features for the vessel detection. So an analyst could look at this and say, yes, this is this type of ship, this is what its presence could potentially indicate in port, and then start doing some pattern of life analysis to say, how is this port being used, and what could this indicate about the region? We can also do coherent change detection. So we've conducted a number of campaigns. This is an example of about 20 sites that were collected between November to December of last year. And so what coherent change detection is you can take a series of images over time and you can stack them, and then you colorize man-made or even natural features depending on what you're looking for. Fun little rhyme to remember is red fled, blue new. It's really cyan, but cyan doesn't rhyme as well. So red indicates objects that were there originally at the beginning of the time series in your image stack that have since departed, and blue is the reverse, where there's objects that weren't originally there that have since appeared later in the time series in the image stack. So what this can indicate to an imagery analyst is what activity is happening at this site and what could it mean. So you can see in red in this image, there's probably vehicles that were there originally that have since left, and there's active work being done on this building, including adding roof rafters or scaffolding. So you can tell that this site is being used, it's of interest, and then you can make some interpretations about why it might be so active, or if it's not. We can also do cool things with our imagery. So SAR imagery isn't, you're used to seeing electro-optical imagery if you've ever taken like a picture with your phone, right? It's done with photons, things are in the correct colors, they're generally in the correct place you expect. SAR doesn't always translate well like that because we're using radars with light. We can get things like image layover, where very tall buildings can look like they're falling on themselves. You can get some backscattered speckling in very still surfaces like over water. So you can see in the first two images in this set, they're a 9-look stack. So we took 9 images as the satellite was passing overhead in rapid succession, because we have up to a minute of dwell time on our satellites to be able to effectively see an area of interest, versus a single look, which is the second image to my left. And you can see that there's a significantly higher amount of backscatter in the single look, particularly over the ocean region, versus the 9 look. What we can do instead is we can apply a machine learning algorithm, just something you can pull off GitHub, doesn't need to be super interesting. And we can start to smooth out some of that backscatter and make it more equivalent to what you would get in an optical image. What can happen though when you do that is your network can eliminate fine details. For instance, it took off the tail fin of this plane. And so that can make imagery interpretation more difficult because now you don't know what type of plane that is. And that can make it harder to decide, okay, why is the plane there? What's going on? Who could be using this site? So to get around that, what we can do is do a fusion of the original image, even if it's just a single look, as well as the AI or machine learning blended image. And we can take both and layer them so you both preserve those fine scale features as well as smooth out that backscatter and speckling that you can see in a single look image.
Right, so why would IonQ want to acquire a company like Capella that's doing all of this image collection with building SARs? And there's actually some complementary things that we've been working on. So I'll just give you like a couple examples real quick. There are many other reasons to do this, and hopefully I'll get a flavor of this, so you all get a sense of it tonight. But one of the areas on the side of like our R&D, like algorithmic research, is we've been looking into using like quantum convolutional neural networks to see if we could do just one of those things that Sutton was describing is like image change detection. So we get now this nice synergy where we get to work with Capella and potentially collect some images and test some of what we're doing with our quantum algorithm on like real world data that matters. And in a very interesting application space. So that's exciting. Another area that we've been looking at is maybe in some situations where your data poor, you don't have many images, there's some motivation to produce like synthetically produced images that you can then use for further analysis or training of some machine learning model, something of that nature. So there are multiple things that we're starting to do with images, detection analysis, and this sort of synthetic image generation as well. It's just an example. Some more examples would be, beyond algorithms, what we're doing now via this another acquisition of a company called Vector Atomic. Vector Atomic builds atomic clocks, inertial sensors, these quantum sensing units with the intentionality of making them highly deployable, right? So a lot of the most sophisticated atomic clocks and inertial sensors, things like this, that have these high sensitivity measurements that one might want to take for different applications, typically sit in labs, giant labs run by a number of postdocs and grad students, and the operational expenses is pretty high, and they're not deployable. So there's been some effort to try to consolidate that functionality and put it in a box. It's like a lab in a box kind of method that you could maybe then deploy. The problem with those is even when they take the lab in the box, they may be able to transport it away from the lab, but it's still stationary as it does its operation. It can't do the operation of any of these like sophisticated sensitive detections under motion. So what Vector Atomic has done is they tried to condense down these quantum sensing units and make it to where you could deploy them in various arenas. And they're actually demonstrating this. So they've demonstrated that they can put a gravimeter on a ship while it's at sea, take measurements, show how it performs. They're doing similar kinds of things with their optical clocks, where they can, have a very performant, robust optical clock, certainly for the size that it is, and put it on a plane, and it still performs well. And then with these gyroscopes, they actually have sort of hardened them and prepared them to be space ready to actually be able to withstand going through launch to get out to a satellite, be deployed on a satellite, and help with some of that orientation detection for things like rotation. So these are actual demonstrations of real deployments. Quantum Sensing technology, I would argue, is one of the more mature quantum technologies, right? The defense sector uses these terms called technology readiness levels, or TRLs. So if you have to put, sensing and networking with computing, I would put sensing as like the highest TRL, right? It's actually deployable systems that are going out there doing quantum things, right? They're, some interaction with an atom and you get measurements from it and it's sitting in a system doing a real application. Networking is then coming next, right? It's kind of like a tier down from that in technology readiness level. You've seen that we're deploying these things. There are existing networks, but it's still in the early days. Like these are small networks, we need to expand them, we need to show a lot of those capabilities. And then quantum computing is taking the longest, right? It's very difficult to build quantum computers, but now we believe that we have a clear path to do so. So you can go to the next slide. One of the things that the Vector Atomic folks are working to do is in the case of like their atomic clocks. So they showed that their atomic clocks have these very high performance and slower drift than a number of other, actually comparable with some of those like lab-in-a-box implementations. So with some of the other like leading state-of-the-art techniques to do this timekeeping. And so what you would really want to do in the case for satellites is help to enable GPS, right? GPS is ubiquitous, it's used all over. You want to have the most precise, accurate timekeeping that you can have to enable that GPS. And right now what they're doing is like there's actually at the US Naval Lab, they're sitting with these like cesium clocks and they have some ground station that will link up with a satellite. And they get up to like, because they're using RF, so they're only getting a precision up to like in the nanosecond regime. Around like 10 nanoseconds, you get a distance resolution of roughly like 3 meters, right? So if you're actually thinking about like operating an autonomous vehicle via like some link to a satellite, you get that precision of roughly like 3 meter resolution. And so what we want to do is, you go to the next slide, is move to these optical links, because in the optical links and these optical atomic clocks, we'll be able to get on the order of like femtoseconds, right? And we get then 3 meters goes to 3 millimeters optical, distance resolution. And so this is a scheme that they had dreamed up, and they're already talking about how they do it with Capella satellites.
We have a question here.
Oh.
Sorry, I was just curious, like, what do you mean by 3 millimeter positioning? Is it like some sort of like GNSS, like, like position location on Earth? Is that what you mean?
Like,
Because wavelengths don't use, like that.
sorry, what? What
Like,
were you saying?
what do you mean by positioning?
Right, so this is my naive understanding. This is very new to me. I'll just be clear on that right now, because we just acquired it, so I'm trying to learn this stuff very quickly. But my understanding is that there's some amount of resolution where you can determine an object is relative on the ground, right? Based on the timing that you have for the signals that you're sending. Am I off on that, or?
Well, I don't know, I just saw autonomous cars. I was like, I don't think they use that tech, because like, there's a lot of.
Oh, this might just be like a theoretical example of something that will be.
What I was meaning to say is, it's like there's even better like satellite positioning. Like you've probably heard like RTK, like construction sites use it to like plot like landmarkers. So I didn't know if that was like some other trajectory you guys were also considering. Or...
Oh, I don't know. Yeah, not my area of expertise. Maybe Sutton might have some more.
So, I mean, it's interesting you bring up RTK. If I recall, civilian GPS is accurate within a couple 10 meters. So RTK has a degree of, if I understand correctly, please tell me if I'm off, you have to do a degree of on-the-ground positioning as well to be able to get down to that level of accuracy. What's being proposed here is effectively doing GPS level navigation in GPS denied environments down to a 3 millimeter resolution. Does that track with what you're asking, or am I entirely off base here? Yeah.
Yeah, let's talk about it, because that gives me something to go look into and learn about more. I have so much information to consume with our recent 7 acquisitions that we've done. Okay, so we can move on. So we're deploying all these systems. This is just, an example of how they constructed this gyroscope and getting it ready to actually send out into space. So that's the next big hurdle that we're really having to overcome with all of these components now. Now we actually have to hard them, get them ready to where they can go into space. So it changes the configuration of what we've actually built up. But it's a very exciting time to do so. And now Capella is becoming absolute enabler in being able to start to explore getting these components out to space for communications, for sensing, and all these things. Okay, so the last thing, and this is just more on potential applications for vectoratomics. We can go to the next slide. The last thing that I want to end on is to just give you this sort of diagrammatic picture of some of the things that you could think about how these components come together, right? Now that we've shown that we have the quantum computers for our node, we have things that can do like quantum frequency conversion. We of course have ring resonators. We have the repeaters and the memory modules. We have the switches. We have all the components that we need then to create these networks for various application spaces. And sort of one of the next arenas that we'll start to explore is this free space optical links, and we'll do it for the satellites. You can do satellite to satellite, satellite to ground, and so forth. And we'll also be doing it with drones. Another announcement that we had announced recently is a partnership with a company called Haven that builds drone technologies. And we want to be able to build these same kind of free space optical links to connect to drones as well. And there's a lot of like defense reasons to do this, and maybe some commercial ones additionally. One of the most exciting things to me, and this is very conceptual, I've worked on proposals in the past that tried to dream up how to do this kind of thing because it hasn't really been demonstrated, is this idea that if we have quantum sensors and we're strictly working with quantum information, then can we keep the quantum information from the sensors quantum? If we keep it quantum, can we share it in a quantum communication line with the quantum computer so then you bypass that classical data ingestion problem that we were talking about earlier, and you're starting to do something that is just entirely unexplored, is doing computation directly on quantum data. It's really interesting, but I don't know of any clear demonstrations of this sort of thing yet. But I think it's exciting. So this is just a general overview of these different potential capabilities, but this is just a subset. There's potentially a large number, and I hope that students sitting in this room are ideating, and this is very stimulating to think of all kinds of different applications you start to do with technologies that haven't existed till today. That's all we have. Thank you so much.